Acceleration in 2D. In one dimension, acceleration, the average acceleration between two events, was defined as the rate of change of the velocity between those two events. In 2D, the definition is the same. It's the rate of change of velocity between the events, but velocity is now a vector, so our average acceleration is a vector as well. And it has two components. The x component, as you might expect, is the rate of change of the x component of the velocity, and the y component of the average acceleration is the rate of change of the y component of the velocity. The direction of this acceleration vector will be parallel to the direction of the change in the velocity vector. Just like the average velocity between two events is parallel to the direction of the displacement between those two events. So there are two ways that a velocity can be changing. Any change in a velocity means the object is accelerating. Here are the two ways. An object is accelerating if its speed, that is the magnitude of its velocity, if the speed is changing, that means it's accelerating, or if the direction of the velocity is changing, even while the speed is remaining the same. If the direction of the velocity is changing, that's also an acceleration. Or, of course, both the speed and the direction could be changing. Let's look at two examples, one in which the speed is changing but direction is constant, and one in which the direction is changing. Direction of the velocity is changing, but its speed is constant. Okay, example one. So here is a map, y versus x, and an object moving in a straight line path. I've noted its velocity at 2 moments. Here at t equals 0 seconds, and here at t equals 1 second. So that its velocity at that time, and we can see that 1 second later, its velocity has changed. The direction is the same, but the magnitude of the velocity has increased. Its speed has increased. So it started out slow and is going faster here. By comparing the two arrows, we see that this one is about 1/3 the size of this one. So its speed has tripled from 0 seconds to 1 second. I've noted the values of the components here. So initially t equals 0 seconds, its Vx is 4, Vy is 3, so the magnitude is 5 meters per second. And that angle there we get by taking the arctangent of Vy over Vx, so 37 degrees. Then at this next moment, we can tell just from looking at it that the speed had about tripled, which means that if the speed is tripled, the hypotenuse is tripled, then the components have tripled as well. Vx should be triple, and Vy should be triple. So Vx is now 12 meters per second, 9 meters per second, and our speed, that is the magnitude of the velocity, is 15 meters per second. But if we take the arctangent of this ratio, the ratio has stayed the same since both sides tripled, so our angle here is the same, 37 degrees. These are two similar triangles. Okay, now let's look at the average acceleration between these two events. The x component of it will be the change in Vx over t. Well, so that's final Vx, 12 minus initial, 4 meters per second. And the change in time was 1 second minus 0 seconds. So that comes out to be 8 meters per second 8 meters per second squared. Our average, the y component of the average acceleration, delta Vy, so that's 9 minus 3 meters per second over a time interval of 1 seconds. That is 6 meters per second squared. What these components tell us is that the x component of the velocity increases by 8 meters per second every second. So in the passage of 1 second, our x component went from 4 to 12. It increased by 8. And in the y direction, it increases, the y component of the velocity increases by 6 meters per second every second. So in 1 second, it went from 3 to 9 meters per second, it increased by 6. Okay, and then the magnitude of the average acceleration we get by squaring and adding and taking the square root of the components. That's going to come out to 10 meters per second squared. And the angle, the arctan of that ratio, 8 over 6, that's going to come out to be the same, 37 degrees. If we draw in our average acceleration, let's see, the x component is 8, y component is 6, so 8 and 6, we should find that our average acceleration vector is parallel to our velocities, parallel to our path. If we're moving in a straight line, the acceleration is going to be parallel to that line, just as the velocities are. And that angle, 37 degrees, we showed here is the same as this angle here, 37 degrees. They are parallel. Okay, that is speed changing, but direction staying the same. The next example is with the speed staying constant, but the direction changing. So this time on our map, the path of our object is sort of a semicircle. It's moving on this curving path. It's taking this curve at a constant speed. So I've noted its velocity at time equals 0 and time equals 1 second, and their magnitudes are the same. The speed hasn't changed, but the direction of the velocity has. Okay, is it accelerating in this case? Naively, you might say that if the speed is the same, then no, it's not accelerating. But we're about to show that if your direction is changing, you are accelerating. Okay, let's look at your components here at 0 seconds. Here, Vx is 3 meters per second, Vy is 4, so our magnitude is 5 meters per second. Then, as we go through the curve at this moment, Vx is now larger, it's 4 meters per second. Vy is now a negative 3. It started out as a positive 4, and now you're moving down. Your y-coordinate is decreasing. Vy is a negative 3. Such that the magnitude of the velocity, that is your speed, is again 5 meters per second. It's the same. Speed hasn't changed. Let's look at your acceleration. The x component of the average acceleration, delta Vx, that's going to be 4 minus 3 meters per second over a time interval of 1 second. So 1 meter per second squared. The y component of the average acceleration, delta Vy, let's see, that's negative 3 minus 4, final minus initial, negative 3 minus 4 meters per second over 1 second. That is negative 7 meters per second squared. And then the magnitude of the acceleration given these two components is going to be about approximately 7.1 meters per second squared. Okay, clearly we have an acceleration here. The x component of the velocity is changing. It increased at a rate of 1 meter per second squared, and the y component decreased. It was positive, it had to go to 0 and then become negative. So it changed by negative 7 meters per second every second. Let's try and draw in this acceleration vector. X component is 1, y component is negative 7. So negative 7, 1. Our average acceleration between these two events, a average x component, y component. The average acceleration is pointing down in this direction. What that's telling us is that the velocity changed its direction. It was pointing up this way, and this acceleration sort of caused the velocity to tip this way to meet our new velocity. Since our acceleration wasn't lined up with the original velocity, it changed the direction of the velocity to its new orientation. So that's the speed staying constant, but the direction changing.